All right, we're in business. So I would like to start by thanking the organizers of the Geometry and Topology in Robotics workshop, which is part of the Robotics Science and Systems Conference in this year. I will talk about distortion, which is a geometric topic, in particular the average and the expected distortion, and I'll give meanings to those things during the talk. I'm from IST Austria, which is a new university near Vienna, and this is joint work with Anton Nikitenko. I'll start by giving some intuition that will lead to the more technical parts of the talk. Take, for example, a straight line, like the red line here, and digitize it. And by this, I mean overlay it with the integer grid, or rather the square partition of the plane. And the line will go from one square to the next one in this staircase manner. So whichever square the line passes through, I draw the midpoint and I connect neighboring midpoints by blue edges. And so I get this staircase representation of the line. By distortion, I mean the length of the staircase divided by the length of the line, of the piece of the line that defines this piece of the staircase. And if for a horizontal line, for example, the distortion is 1, the largest value I can get is if the line is 45 degrees or minus 45, in which case I alternate between vertical and horizontal line segments, and then the distortion is roughly square root of 2. That's 1.41. All right, let me do the same experiment for the circle. So in the circle, I alternate again horizontal, vertical, same way as before. But now when you compute the distortion, I can do it in the limit. In the limit, I mean, as the square partition, the squares of the partition get smaller and smaller. And in the limit, the length of the staircase is 8, because I have a length 2 line segments I can see from the top, the same from the bottom, same from the left, and same from the right. And the circle has length 2 pi, so the distortion is 4 divided by pi, so that's 1.27. And it doesn't really matter where I put the circle. So different from the line segment is that this, for the circle, this constant is independent. And indeed, we'll see that this distortion constant, 4 divided by pi, is universal in some sense. Let me do the same thing just to get used to it in 3 dimensions. There I call this the staircase a stair-scape. So when I take a plane, again, least distortion is 1. The maximum distortion I get when I take the plane normal to the diagonal vector 1, 1, 1. In which case the distortion is square root of 3. And you see the arrangement that you get in this case. So this would be a representation of a piece of a plane in 3 dimensions. So it's between 1.0 and 1.73. And if I take the sphere, which I did not dare to draw anymore, but I can give you the constants, because the area of the sphere, as we know, is 4 pi. The area of the stairs in the limit, again, when the cubes get smaller and smaller, is 6 pi, because from all the coordinate directions, the sphere looks like a disk. The disk has area pi, so I get 6 times pi, 2 directions for each coordinate direction. So the distortion is 6 pi divided by 4 pi, so that's 3 over 2. And just like the constant for the circle, which was 4 over pi, this constant for the sphere, 3 over 2, is going to be universal in some sense. Okay, now I want to shed more light onto those constants and what they mean. Here are the constants, the concepts that I need. Instead of going through a set of squares, I'm interested in what's called the Voronoi path And there, the square tiling of the plane is replaced by a Voronoi tessellation of the plane. There I put points down, finite or infinitely many. I partition the plane into Voronoi regions. And the dual is called the Delaunay mosaic. And then the Voronoi path of a line, for example, is the set of Delaunay edges and vertices, which are dual to the Voronoi edges and regions that are crossed by the line. And so here in this picture, you see a window of a two-dimensional Voronoi tessellation through a circular region. The red line passes through a sequence of shaded Voronoi regions. And generically, it passes only through regions and then edges separating neighboring regions. I will, in general, ignore degenerate cases. So I get this path. And then the distortion, of course, would be the length of the Voronoi path divided by the length of the line or a piece of the line. A little bit about prior work. There was not too much. I found 2 papers. To explain this, I'm writing A for a Poisson point process in Euclidean space. Poisson point process, just to remind you, is like a uniform distribution, except that it's not within a compact domain. And also, you don't have to specify the number of points, but the density. In any region, the likelihood that you get a point in the region, depending on the volume. So A is this Poisson point process in D dimensions, and L is a line. And then for this case, namely the 2-dimensional case, in 2000, Bacelli, Chumachenko, and Zuyev proved that the expected distortion of the Voronoi path is 4 over pi. That's the familiar constant we saw for the circle. And I remind you, this is for the case of a 2-dimensional Voronoi tessellation of a Poisson point process. And the line generates the Voronoi path. It's only for lines, it's not for line segments or circles or stuff. And then generalization to higher dimensions came in 2018. De Castro and De Villiers proved that this distortion in D dimensions, again, for a line, a 1-dimensional line, is this expression, square root of 2d over pi plus big O of 1 over the square root of the dimension. So this is for the case of a line in D dimensions, and we have a Poisson point process, and the constant is not exactly known. I'm going to introduce now the constants that we play with, which kind of foreshadowed our results. The main topic here is this d sub p comma d. So that we call this, or I call this a distortion constant. And for the line case, so p is the dimension of the shape that I create the Voronoi path or scape for. So the prior work is all in the first line of this table. Here we see 4 over pi in 2 dimensions, so that was resolved for the Poisson point process case. I will generalize this somewhat to other cases, but now in higher dimensions, we also get the precise constant. So for example, I get 3 over 2 in 3 dimensions. And just as a comparison, the result, the square root of 2d over pi in 3 dimensions is roughly 1.38. So it's rather far away from this. We also get constants for higher dimensional objects. So 2 would be for plane, for sphere, and stuff. And the general formula for this distortion constant is down here. You can think of it as a binomial coefficient, except that the arguments are not integers. They could be half integers. So it's best written as a ratio of gamma functions. Or I like to sometimes write it in terms of double factorials. To remind you, the double factorial is of d for example, is the product from 1 to d, but not every integer, but only every other integer is taken. So d and d minus 2 and d minus 4 and so on. So this is the fairly elementary description of the distortion constant. If you write it in terms of gamma functions, you save the case analysis, the two cases that you need for the double factorial notation. All right, I'm not gonna talk about the methods. Sorry, I'm not gonna talk about the proofs, but I'm gonna talk about the methods that are instrumental to make the proofs work. And one, of course, is the Gradmanian. I write it as GR of P comma D. So P is the dimension of the plane. So the Gradmanian is the infinite collection of p-dimensional planes in d-dimensional Euclidean space. And I require here that all the planes pass through the origin. That's the usual convention. And just to get a feeling for it, if you're not so familiar with the Gradmanians, this is a reasonably high dimensional manifold of dimension p times d minus p. Maybe a case which is easy to understand is the Gradmanian of the lines in 2 dimensions. So that's p equal to 1, d equal to 2. There I'm talking about lines in a plane that pass through the origin. So I get this circle of lines. But when I go through the 360 degrees, I get every line twice. So this is like taking the circle, maybe of the normal vector, and identifying antipodal points. So instead of a simple circle, I get the circle covered twice. If I do this for planes in 3 dimensions, I would get the sphere with antipodal points identified. So that's the 2-dimensional projective plane. All right, so we have this Gradmanian, and then here is the main lemma that I need in order to make everything work. Namely, I consider a p-dimensional unit cube. I project this p-dimensional unit cube, I call E, onto a p-dimensional plane, and I measure it. So I'm interested in a p-dimensional measure of a p-dimensional cube projected orthogonally onto a plane of the same dimension. And then I wonder about the average and also the average of the square. In the plane, when I have p equal to 1, so here E is just a line segment of unit length. This is a fairly easy exercise, because if I integrate over all directions, then I get all these chords through the circle that share the left endpoint with E, and the right endpoint moves on a circle. And then if I take the integral, then the average length of this line segment is 2 over pi. Simple exercise is the area below the cosine function divided by pi, because that's the angle I rotate through. So this also shows up in, for example, in the, what's it called again? Buffon needle experiment, same thing. If I take the square of the length of the projection in a plane here, I get 1/2. And the reason is simple, because the red line segment is symmetric to the dotted blue segment if I go through all the angles. And the sum of the 2 squares is equal to 1 by Pythagoras. So the average squared length of the projection is 1/2. Why do I need this? Because I want to write the distortion constant in terms of averages of these moments. So I do this now in a general case. So I'm going to define the jth projection moment, which is the average jth power of this p-dimensional measure. So E is a p-dimensional unit cube, L is projected on, I take the jth power. And here I don't have the constant that I have to divide by the size of the domain, because I assume a probability measure on the Gradmanian, so that the integral is automatically also the average. And then for this definition, I'm only interested in j equal to 1 and 2. For this definition here, the lemma we have is that the first projection moment is this ratio of gamma functions, and the second is this 1 over the binomial coefficient. Both proofs are very geometric. Short proof, not complicated, and the benefit of that is then the distortion constant is the ratio of the first moment over the second moment. It's a little exercise to prove that this is in fact true, that if I take this ratio divided by the second moment, I get the constant that I showed you earlier. But you can do it. All right, so now more to the geometry of the proof. A key concept is that of a tile. So a tile is a partition of a reasonably high dimensional space. And each point of this space is a point in Euclidean space and the line. So it's a point and the line pair. And here is how I collect point line pairs into tiles. So this annulus kind of shape is the projection of a tile into the Euclidean space. Let me explain. We're given a Delaunay simplex gamma. Here's an edge. There's a dual Voronoi polygon gamma star in the plane is also an edge. Whenever I pick a point on gamma and a point on gamma star, I have a unique circle, the smallest circle that passes through those 2 points. And the points on this circle have the property that when I draw a line through the point on gamma star, the projection of the point on gamma is this point on the circle. All right, so let me get to the definition of a p-tile. So I'm taking a p-dimensional Delaunay simplex, d minus p-dimensional dual Voronoi cell, and I'm talking about all the point line pairs such that the line L plus X intersects the Voronoi polyhedron, and the point X projects onto the point X is in the projection of the Delaunay simplex onto this line. So this in some ways represents all the different Voronoi paths that I can create where gamma is in the path because gamma star is intersected by a line. And just to double check that we're in the right path, the dimension of this tile is d plus p times d minus p. So the second part was the dimension of the Gradmanian. And what you see here in the picture is a projection to d dimensions. All right, so we would decompose the whole space with these tiles. For each tile, since the circle really represents all the possible rotations of my plane, I know the average distortion because that's I computed earlier. So if I can tile the whole high-dimensional space into these tiles, automatically I get the average distortion as I gave you, the distortion constant. There's still a problem with proving that the average distortion is the same constant or the expected distortion. Namely, I would like to prove that the constant as follows. I would take a large part of space, d-dimensional space, namely a ball, and then do the computations inside. And then I increase the ball, let it go to infinity, and then I show that in the limit, I get this constant. The trouble is with the limit consideration, because as I get bigger, I intersect more and more tiles, which is fine. But depending on the point distribution, those tiles might get very large. The point distribution might be very uneven. And at any moment, my ball contains some of the tiles in the projection, but then there are some tiles which are only partially inside and they're partially outside. And if they're partially inside and outside, then I don't know what exactly the average contribution is. So we're gonna assume that the point set has a property that the tiles that are only partially touched don't have a big contribution. We call this the mixed regularity property, and it says that the boundary tiles, which are exactly the ones that are partially inside and partially outside of this ball, have a measure which is smaller than the volume of the ball. For example, a Delaunay set has this property. So if there exists a radius R0 such that every ball that is of this radius contains a point of my set A, then I have the mixed regularity property. Also, the Poisson point process has this mixed regularity property in expectation. All right, and with this, I can then now formally state the results. I'm gonna state two results, one for the average, one for the expectation, and then I'll show you some experimental results. For the average distortion, what I'll take is a set A that has the mixed regularity property. I take a p-plane L and a subset of this p-plane, maybe a line segment or a disk or something like that, which is rectifiable, but a p-dimensional subset. Then the average p volume of the Voronoi escapes of the congruent copies of omega. So what I have is omega, and then I look at all the possible positions of omega inside of a big ball. Then the average distortion is d sub p plus d plus a small error. So the average p volume is the original p volume times this constant plus a big O of one term, as the radius of this ball goes to infinity. So this is for the average distortion, and for the expected distortion, I use a Poisson point process. Now, the reason for a Poisson point process, well, there's several, but one is Poisson point process is symmetric with respect to translations or rotations. So I don't need to change to look at congruent copies of my shape omega. I just take a fixed one, and then the expected value is the average value of all these possible positions. And therefore, I can also generalize to shapes which are not flat. So the assumption here is I have a compact, smoothly embedded p-manifold, which includes circles and spheres, but more complicated things. Then the expected p-dimensional volume of the Voronoi escape maps to the original volume times this constant that I told you. It's more or less a corollary of the average theorem with some complications. And one of these complications will show up in the experiments that I show you now. So here I'd like to thank Anita Biswas and Tanya Ezubova. We did experiments for all kinds of things. I'll show you only two, namely in a plane, a circle. So given a circle, this is the Voronoi path. And we sampled different sizes, different densities. So the Voronoi tessellation is that of a Poisson point process with different densities. It's all stationary. Here's the number of points. They're not integers because we averaged over, I think, 1,000 experiments. So for each density, we did 1,000 runs and then average everything. And here the third column is the average distortion that we find. And so you see it's very close to the predicted distortion already for less than 100 points. And then it converges quickly when the number of points goes bigger. On the last column, we have the standard deviation, which you see shrinks. And I need to explain the second column, the number of leaves. So a leaf is when in a reconstruction of the circle, you get a branch coming off the main circle. And for the line segment, this doesn't happen. But for the circle, it could happen that the circle intersects a Voronoi edge in 2 points. And then I would get an edge, but the dual edge is a Delaunay, and then I come back on the same dual edge because I intersected a second time. More generally, I could have a tree growing. So the homotopy type of the reconstruction is that of a circle, but homeomorphically, they're not necessarily the same, even if you sample very densely. But you see that the number of leaves actually does go to 0 as you sample denser and denser. But there's always a chance of having some. And even though there are these leaves, which are then double counted in the length, the predicted constant is the one that you get. And the second experiment I want to show you is a similar experiment in space. I have a curve. This time we took a trefoil knot. We took the Voronoi path. Again, it's guaranteed to be homotopy equivalent for dense enough sampling, but not homeomorphic because there could be leaves. Here the leaves also go to 0, the number of leaves, but not quite as fast as in the plane. We see the distortion constant, so mu is the average, so it's 1.544 already for 51,000 points, which in 3 dimensions is not so much. It's at 1.5, not distinguishable anymore with 3 digits out after the comma. And with this, I thank you for listening. Oh, I need to introduce the next speaker. So the next speaker is Philip Maric from the Institute for Aerospace Studies of the University of Toronto. And he will speak to you about ellipsoids and distances, in particular, using this as a motivation to reconsider robot kinematics. Thank you very much.